So last time we discussed setting the metric equal to flat space with a small perturbation, and then we studied the equations for that small perturbation. And as I mentioned before, that perturbation represents gravitational waves, which are distortions in the metric that travel at the speed of light. So we picked a gauge or coordinates harmonic gauge, and when you work this out to first order in H, it looks like this. So that's four gauge conditions or coordinate conditions. And as I explained, it doesn't fully fix the coordinates. It still leaves some residual coordinate freedom. So I can still change coordinates provided I leave that condition unchanged, the gauge condition unchanged. And so then we discovered that the Einstein equations, in the absence of matter, these become box h mu nu equals 0 in this gauge. And so the solution was sum over, and let's just write it out in this way. It's a sum over wave numbers, k. This equation here becomes the condition k naught squared equals k squared. And so I can write the solution in the following way. Epsilon mu nu of k. This is the spatial wave number times e to the I k dot x. And if you ask what is this exponent, if we write it out explicitly, it's the magnitude of k times t minus k dot x. The energy, the sort of k naught component has to be k naught squared equals k squared. Okay, so this is the general solution of the wave equation. It's a linear, so the way to think about it is I first Fourier transform with respect to space. Okay, so this is equal to e to the I mod k t minus k dot x. So I first Fourier transform with respect to space, and then I discover that the Fourier modes evolve harmonically, in other words, as e to the I kt with time. So these are plane waves, of course, and we can have waves just as we did with light. We can have waves which look like epsilon mu nu as a function of, let's say, x minus ct, with some appropriate conditions, with various conditions on these epsilon mu nu, which we'll study. But basically, this is a tensor function which is traveling along as a wave, and that will satisfy the wave equation. And then we have to think carefully, what does this condition mean for that function? And do I have any other coordinate freedom? What we'll discover is that using the gauge condition and coordinate freedom, if the wave is traveling in the x direction, then epsilon mu nu must be transverse to the wave, i.e. if wave travels in the z direction, the only non-zero components are epsilon xx, epsilon xy, epsilon yy. And when I say the only non-zero components, what I really mean is you can pick a gauge in which the only non-zero component. So basically this epsilon is, you can change it with coordinate transformations. But what I'll show you is that you can pick your coordinates so that the wave's going along in one direction and the only non-zero components of the gravitational wave are in the perpendicular directions. And that's why we call it a transverse wave. Okay, so let's show that. So I've got my h mu nu equals to a sum of epsilon mu nu. These are constants, they just depend on k. So let's write them as functions of k, e to the I k dot x. This is space-time dot e to the I k dot x plus complex conjugate, because the metric is supposed to be real. And that solves the Einstein equations. And the gauge condition reads, k mu epsilon mu nu, k mu epsilon mu nu minus a half k nu epsilon nu mu equals 0. Okay, so that's obvious from there. The partial d by dx lambdas just turn into k's because of the Fourier transform. And now, as I explained, I'm still free. Probably. Yeah, thank you. Mu. Thank you.
I mean, otherwise they cancel.
Yes, that's true. Yes, you're right. You're right. There's a nu here. Yep, thanks. Okay, the free index is the nu. Okay, so we are still free to change coordinates. And as long as we maintain the gauge condition, okay, so you'll remember that when I change coordinates, h mu nu goes to h prime mu nu, which is h mu nu minus epsilon mu comma nu minus epsilon nu comma mu, where epsilon nu is any four-vector function of space-time. So this generalizes the gauge transformations in Maxwell's theory. And in particular, you see, I'd like the h prime mu nu still to satisfy box h mu nu equals 0. So the easy way to do that is to have epsilon itself be a sum. So in particular, if epsilon mu of x is a sum, and I'm going to just change from epsilon to c so we get less confused. Epsilon mu nu has nothing to do with epsilon mu nu here, right? These are vectors. This is a tensor. So I'm going to choose the expansion coefficient to be c. I'm going to put an I here just to make the equations a little nicer. E to the I kx plus complex conjugate. So if epsilon mu is equal to this, where c mu is a function of k, and again, if you think about it carefully, c mu is only a function of the spatial k, because the k naught is given implicitly by k naught equals modulus k. Okay, so that's going to be my coordinate transformation. And when I make this coordinate transformation on H, you can see from here and here that all that's going to happen is I'm going to change my epsilon tensor by something involving C. Okay, so this has the effect that epsilon mu nu goes to epsilon mu nu prime, which is epsilon mu nu plus, you see when I differentiate, I'm going to get an I k nu, and then that I multiplied this I will give a minus sign, and that'll cancel that minus sign. So I'll get epsilon k mu c nu plus k nu c mu. Okay, so coordinate transformations which themselves obey the wave equation So coordinate transformations which themselves obey the wave equation just have this effect of shifting the polarization tensor epsilon. And we can use such transformations. Now let's see. It should be that these transformations leave the gauge condition invariant. We can check that. Okay, so let's calculate let's calculate this k mu epsilon prime mu nu minus a half k nu epsilon mu mu prime. So the first term is 0 because epsilon solved the equation. And the second term gives me this one will just give me k squared when multiplying by this. This will give me, and k squared is 0. So over here, I'll get k dot c, k nu, from this second term. And then minus here, k nu here, times 1/2. And then epsilon mu mu, I get twice k dot c. Right? So this gives 0. So these type of coordinate transformations leave the gauge condition preserved. And so the counting is as follows, that I have on the first line of that blackboard, I've got 10 functions, h mu nu. These gauge conditions are 4 equations, so that subtracts 4. I have 6 linearly independent epsilon mu nu. But I still have 4 arbitrary c nus. Okay, so 10 minus 4 gives 2. So we end up with 2 linearly independent entries in that polarization tensor matrix, which cannot be changed by coordinate transformations. So let's sort of see that all explicitly. So let me just write that down. The 10 components of h mu nu get reduced to 6 by the gauge condition, and down to 2 by the 4 remaining coordinate transformations, which preserve the gauge condition. Okay. Yeah.
I was getting confused by the terms floating around up above. Now you've got an epsilon mu, you've got an epsilon mu, and one of them's a polarization tensor, and the other one is the Florida transformation.
Yeah, this came from exponential.
But then over on the right-hand side, like you see mu.
Yes. C mu is a Fourier coefficient of the coordinate transformation.
I'm just trying to see where you got that down, then pulling out a polarization tensor on your last.
This one?
Like the line below.
Okay.
Where that came from, yeah.
Okay. So, are you happy with this? We can change the polarization tensor with these C mu's.
Yes.
Fine. Now, what I'm checking below is that if I do this change, it leaves that gauge condition respected. So what I did is I plugged this formula into the gauge condition, right? And this is what it's equal to. And what you see is that if epsilon mu nu satisfies the gauge condition, then so does epsilon prime mu nu, because this extra term doesn't change anything, right? The change in the gauge condition comes from here, but these terms precisely cancel between this one and that one. That's what happens, okay? So epsilon prime mu nu dotted with the k. First I got a k squared, but k squared is 0, okay? Then I got k dot c times k nu. That was this first term. And this term, I take the trace of this guy, the mu mu, and that gives me twice k dot c, and that exactly cancels. Okay, so let's just do this all explicitly. It's worth doing. So let's pick our form momentum to be this. Okay, so this represents a gravitational wave y, z, a gravitational wave traveling in the z direction. Okay, so obviously e to the I k dot x will be e to the I k t, so actually with a minus sign, right, will be e to the minus I k t plus I k z. And this will lead to, well, I can write that as e to the I k z minus t. And so this represents a wave propagating in the z direction. Okay, so it's some wave-like pattern in z, and the pattern just shifts according to by t as the time evolves. Okay, so that's our wave. K with downstairs indices is minus k, 0, 0, k. Let's write out explicitly this equation, k mu nu epsilon mu nu is 1/2 k nu epsilon mu mu. So for nu equals 0, we have k times epsilon 0, 0 plus epsilon 3, 0 equals minus 1/2 k. Then the trace of epsilon, I have a minus sign in the 0, 0 component, and 1, 1, 2 plus epsilon 3, 3. Then I have k, so nu equals 3. Let's let's write this down, 0, 3 plus epsilon 3, 0 equals plus a half k minus epsilon 0, 0 plus epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. And then I have 1, so k times epsilon 0, 1 plus epsilon 3, 1 equals 0. And 2, I have k times epsilon 0, 2 plus epsilon 3, 2 equals 0. Okay, so these are my 4 equations for the 10 components of epsilon. And what we see from this is epsilon 0, 1 is minus epsilon 3, 1. Epsilon 0, 2 is minus epsilon 3, 2. Epsilon 0, 3 is equal to minus 1 half. Epsilon 0, 0 plus epsilon 3, 3. And epsilon 2, 2 is minus epsilon 1, 1. Okay, so we've managed to eliminate 4 components of epsilon using the 4 gauge conditions.
In the second line of mu equals 3.
Yes.
Epsilon 0, 3 plus epsilon.
Oh, I'm sorry, you're right. That's 3, 3. Thank you. Okay, now we have the residual coordinate freedom, i.e. this C mu, and that gives us epsilon prime mu nu is epsilon mu nu plus k mu c nu plus k nu c mu. And so this gives us epsilon 0, 0 prime is epsilon 0, 0 minus 2k c 0. Epsilon 1, 3 prime is epsilon 1, 3 plus k c 1. Epsilon 2, 3 prime is epsilon 2, 3 plus k c 2. Epsilon 3, 3 prime is epsilon 3, 3 plus 2kc3. And we're free to pick C0, 1, 2, 3, whatever we like to be, whatever we want them to be. So we can choose C mu so that epsilon 0, 0 prime equals epsilon 1, 3 prime equals epsilon 2, 3 prime equals epsilon 3, 3 prime equals 0. Okay, so, and now from these equations, all of these other terms are 0. So basically, this means that epsilon mu nu is a matrix which is 0 almost everywhere, but in the 1, 2 components, it is not 0. Okay, that's all that's left. Epsilon is symmetric matrix, so epsilon 2, 1 is the same as epsilon 1, 2. And epsilon 2, 2 is minus epsilon 1, 1. Okay, so we're going to actually define this to be the following. Epsilon plus, and then minus epsilon plus. This is the polarization aligned with the 1, 1 and 2, 2 axes. And then we're going to call the other guy epsilon cross and epsilon cross because it involves both 1 and 2. Yep.
Epsilon prime, like the epsilon prime equation at the very top is 0, 0. Does that just fall out of the math? Or just
Sorry, say the question
like
again.
just your 4 equations, you got like 1, 3, 2, 3, 3.
Yeah, just
0,
here.
0, 0.
I'm just reading off mu equals 0 in this equation. So I get 0, I get the same components here, right? And remember this k mu is lowered index, so it's minus k 0, 0, k. Yeah, I only chose 4 components because there are only 4 of these c's. And there are lots of other components, but these are the interesting ones. Okay, so these ones are enough to allow me to fix the c's by eliminating all of those. Okay, so by choosing a gauge, you can always put your polarization tensor in this form. And this is called transverse traceless or TT gauge. Traceless. So transverse traceless means that the only perturbations in the metric are with indices which are transverse to the direction the wave is moving in, and traceless, obviously the off-diagonal part is traceless. The diagonal part has to satisfy that this is minus that to be traceless. Now we can also define epsilon right. This would be, you see, these are linear polarizations. In one polarization, the H up and down in the H in these two components are non-zero. In the other polarization, the yeah, actually, I'll give you a picture of it later. But for the moment, just allow me to define epsilon right, which is epsilon 1, 1 minus I epsilon 1, 2, which is epsilon plus minus I epsilon cross. And epsilon left, which is epsilon 1, 1 plus I epsilon 1, 2, which is epsilon plus I epsilon cross. Now, if you do rotations, so under rotations, which leave k mu fixed. Okay, so k mu is this 4 vector, but it has a spatial component in the z direction. Okay, now it's clear that if I do a rotation around the z direction, it doesn't change k. Okay, that's called the little group of k. It's the subset of Lorentz transformations which leave the 4 vector alone. And what we have in H mu nu is some representation of the Lorentz group. If you've done group theory, you'll realize that the H mu nu has to transform under the Lorentz group. And it's interesting to ask, how does this gravitational wave change when we do rotations in this little group? So here's my k vector. And if I do rotations about the z-axis, I'm going to transform 1 into 2. And I'm going to transform these components of H, the 1, 1 component into the 1, 1, and into the 2, 2, and the 1, 2. They're all going to mix under these rotations. So it's interesting to ask, how does this polarization change if I do a rotation around the z-axis? So under these rotations, we have epsilon pi mu nu will be cosine sine theta minus sine theta. I'm just going to do the 1, 2 components. Yeah, I guess I'll just write them down. Epsilon 1, 1, epsilon 1, 2, epsilon 2, 1, epsilon 2, 2 prime. These are given by cosine theta, sine theta, minus sine theta, cosine theta, times epsilon 1, 1, epsilon 1, 2, epsilon 2, 1, epsilon 2, 2, times cosine theta, sine theta, minus sine theta, cosine theta, transpose. Okay, why? Because epsilon is a symmetric tensor, okay, and epsilon mu nu prime is equal to lambda epsilon lambda transpose. Okay, epsilon is a symmetric tensor, and so under Lorentz transformation, that's how epsilon transforms. Okay, it has two indices, they both transform with a lambda, and you remember when we write this as a matrix, we have to transpose the second one. So you can work this out very easily. It's a complicated expression, but the result is that epsilon right prime, this guy defined here, is equal to e to the 2I theta epsilon right. And epsilon left prime is equal to e to the minus 2I theta epsilon left. Okay, so there's a theorem in group theory that when you have an abelian group, like this little group of the 4-vector K, that if you have something which transforms under that group, you can split the representation into block diagonal pieces, and each piece must be one-dimensional. Okay, the only irreducible representations of an abelian group are one-dimensional. Okay, and that means they're just a phase. So group theory guarantees this is going to work, and the answer is that gravitational waves have this number 2 in the exponent. Okay, and that means they are spin 2. If you did the same thing for a photon, it only has one index in the tensor here. When you do this transformation of a photon polarization vector, you just have one of these matrices here, and you'll find the two polarizations of a photon have spin 1. Okay, there are only two independent degrees of freedom in the photon solution, and they have spin 1. So this means that the graviton has spin 2. All right. Likewise, if you did this for a fermion field, like a Dirac field, which I think you'll do later, you'll find the exponent is a half. When you rotate it, it only changes by e to the half I theta. That's because you don't use these Lorentz matrices at all. You use the spinor representation of the Lorentz group. Let's see if this has been fixed. No. So these are the left and right polarized gravitational waves. That's why I called them L and R. Yep.
So this means that
I should say circularly polarized.
Turn 180 degrees.
Yeah. Yeah, that's correct. Another way of saying it is that when I think about a gravitational, yeah, that's exactly right. So let's go back to electromagnetic wave. If I look at an electromagnetic wave coming at me out of the board, the electric field is a vector, right? Points in some direction. So I can picture this wave as being specified by the direction of this vector. This vector could point anywhere, and all those waves are different for an electromagnetic field. The gravitational wave is totally different. The gravitational wave I should think about as a headless vector. Okay? You see, when it squeezes space, it's squeezing it in this direction, but it's both squishing it that way and squishing it this way. There's no directionality to it. Okay? So if I turn the gravitational wave upside down, it does exactly the same thing. It just squeezes it. It's compressing, and I turn it upside down, it's still compressing. And so this is a headless vector. Okay? And a headless vector is a spin 2 representation of the rotation group. So yes, you should think about gravitational waves as headless vectors. In fact, I digress a little bit, but if you, this is something I worked on a while ago, but you know about liquid crystals. Your LCD displays are made out of liquid crystals. And what are liquid crystals? The liquid crystal is just a liquid made of rod-shaped molecules. Okay, so they are just rods. Okay, like this. And they don't have a directionality. Okay, so it turns out that when you describe this, the way a liquid crystal orders, so for example, if all these rods line up, you have to take into account the fact that this rod is invariant under 180-degree rotations. It really doesn't have a direction. And this is crucial, in fact, to understanding the system, because you can have string-like defects. You see, if you have an arrowed vector, like this, I really am digressing, I'm sorry. Okay. But an arrowed vector can have defects like this, where at this point, if the vector field is going to be smooth, it has to vanish. Right? That's a topological zero of the vector field. It says that if the direction of the vector field changes around 360 degrees, it just has to vanish somewhere. Okay? Whereas if I have a headless vector, there's another option, okay, which is that I'm not sure I can draw it. I've only got to change by 180 degrees as I come around the defect. Okay, so when I come down here, it will be like this, and I guess it's going to tilt that way, and here's my defect. And that is a perfectly continuous field, which has, have I done it right? Yes, I've done it right. So as you go around, right, it changes continuously, but only 180 degrees. No. Like this, and then like that. Okay? So this is very important, because when you make an LCD screen, you get defects. Okay, you try to line up all these liquid crystals, first thing that happens, you get these defects, and they can't be removed because they're topological. All right? And it turns out the defects are kind of half defects. And you may have heard buzzwords of Majorana fermions and all that kind of stuff, and this is related to that. I won't attempt to go there. But yes, a very important point that gravitational waves are really headless vectors, which are spin 2 objects, not spin 1. Okay, so just for fun, we did this in 4 dimensions. Yeah.
Can you explain again why that 2 in the exponent implies it has spin 2?
That's the definition of spin.
Definition of spin, yeah.
Look at all the representations of the Lorentz group, or the rotation group, and you find that they come in half integer. Okay, it's consistency of the, it comes from the commutators of the rotation group, that you're forced to spin half. You know, when you did quantum mechanics, all you're really doing is group theory. And when you showed that a spin half particle you showed that the representation of the commutation relations, right, had to be Jz equals, well, I guess you showed J equals 1, well, I guess 0, half, 1, etc. One can show that from the commutation relations of the spin operators. And these numbers are precisely the numbers which appear in here. It's the same group, because just the rotation group. Of course, you're using the fact, you see, I singled out the xy direction. If that's all I knew, I wouldn't be enough to specify that these had to be half integer. I need to know that this xy direction is a part of the full three-dimensional rotation group. Three-dimensional rotation group is this non-abelian guy that has quantized spins. So that's where this comes from. Yeah.
So you said you were taking the little group of something? What were you taking the little group of?
Oh, the little group of the... So consider all the lambda mu nus, right? All the Lorentz group, which leave k mu invariant.
Precisely, but which is k?
K is the 4 vector.
Well, yeah, no, but what 4 vector? That's all.
Oh, the one I've used throughout. This one.
Oh, this guy over here. Okay.
Yeah. Okay. So I pick a 4 vector, which is this vector going in the z direction. Of course, it includes time as well. I've sort of taken out all the time. And so when you restrict to rotations, you're just looking at rotations which leave this z vector, I guess I should write it as a column, equal to 0, 0, k. And these, the only rotations that leave the z vector alone are rotations around the z axis. And that's what these ones are. Okay, so just for fun, let's think about higher dimensions. Okay, so we in any dimension d, so in d space-time dimensions, so H mu nu is a d times d matrix, and so that has d plus 1 over 2 components. Right? It's a symmetric matrix. So there's d minus 1 over 2 off-diagonal elements for a symmetric matrix. And then there's d diagonal components. And you add those two up, you get d plus 1, because it's a symmetric. And that's a lot. That's equal to 10 in 4 dimensions. But then we have d gauge conditions. Okay, so we get d plus 1 over 2 minus d. And then we have d residual coordinate transformations. Coordinate transformations. And so I reduce this to d minus 1 over 2 minus 2d. And if you work that out, that's equal to d squared. Let me see. D minus, that's equal to d minus 1. Sorry. That's equal to, according to me, what is that equal to? That's equal to d minus 3 over 2. Is that correct? Yeah, that looks right. And this equals number of independent components of a symmetric D minus 2 times D minus 2 matrix. Okay, why is that? Well, that would be D minus 2, D minus 3 over 2 for the diagonal elements, plus D minus 2. Sorry, did I get that? Why am I getting D minus 2, not D minus 3? Oh, sorry, symmetric traceless. Traceless, I forgot about that. Symmetric traceless D minus 1, D minus 2 matrix. So these are the off-diagonal elements of a symmetric matrix. The diagonal elements are D minus 2, but the trace is 0 as well. Okay, so I actually get D minus 3, and that's exactly this number. Okay, so what's that saying is that when you think about the HIJs, you can cancel off 2 rows and columns, or the H mu nus. You can cancel off 2 rows and columns, the ones that involve the direction of the vector. You just think about the transverse directions. That's a symmetric polarization matrix, and it has to be traceless. So that works in any dimension. And I guess it's interesting to write down some numbers. So in D equals 2, the number of degrees of freedom in a graviton and the number of degrees of freedom in a photon. Okay, so D equals 2. This expression here is minus 1. So there's certainly no degrees of freedom in a graviton. In a photon, there are 0. Number of degrees of freedom of a photon is just D minus 2. This one is D minus 3 over 2. In 3 dimensions, you have no gravitons. You have 1 photon polarization in 3 dimensions. In 4, we have 2 and 2. In 5, we have 5 and 3. And in 10 dimensions, which some people like, there are no fewer than 35 gravitons and 8 photon polarizations. Yeah.
What does it mean that we have -1
It means we did something wrong. As we saw in, you just means to go back to the beginning and you'll find that you made a mistake somewhere.
It has no physical significance.
Not at all. Not as far as I know. But having said that, one shouldn't be altogether so glib. Sometimes it is useful, especially in quantum field theory, to think of the dimension d as a variable. This is done in dimensional regularization, for example. And in that case, you really are considering the whatever you calculate as a function of d. And it's very useful to actually continue that argument d to unphysical values. Okay, and then you may calculate the function in that region where it's well defined, and then get the answer as a function of d, and continue it back to the physical value. That's a method of regularization, which is very powerful. Yeah.
Just to be sure, when you have number of residual coordinate transformations and you're taking away the second d,
Yes.
you should have d plus 1.
I started with this.
Yes.
I took off one d
Yes.
for the gauge condition. I took off another d. Oh, sorry. Yeah, you're right. You're totally right. Thank you. Sorry. Okay, so now let us actually look at these gravitational waves and look at what they do physically. People are looking for them now. There are these wonderful experiments like LIGO, these kilometer-long interferometers. And what they're doing, as I said last time, is looking for the motion of the ends of the detector, the masses, 1 kilometer apart. And as this gravitational wave goes through, the length of the interferometer changes just because the metric changes. So let's see how that happens. So detecting gravitational waves. And there's a very nice way to see this, which is, if you remember, we discussed the motion of two particles. We call them test particles. These are particles that are just falling in a gravitational field using the geodesic equation. And then we derived an equation for the separation of those two world lines. Okay, so this world line has proper time tau. I can ask, what is the coordinate separation, the delta x mu, between, in fact, let me just call it, I'll call it, I'll call it delta x mu of tau, and I'm going to call that S mu of tau, the separation for vector. And we calculated, we found an equation for delta x mu that just involved the Riemann tensor. Okay, so when you think about something like the LIGO experiment, ignore the fact that it's being held up on the surface of the Earth. That's to do with the z direction. Imagine the LIGO detector is just two masses, okay, and they are just falling freely in space. And then this gravitational wave is going to come along and move them, displace them in the x direction. So think of the two LIGO masses as these point masses, and they're just following geodesics in space-time. And as I said, of course, they're being held on the surface of the Earth, so that's like an acceleration in this direction, but that's perpendicular to the effect of the gravitational wave. So these two masses obey an equation, the separation vector. So the separation for vector, d2s mu d tau squared was equal to the Riemann tensor nu rho sigma u nu u rho s sigma. And so to understand the effect of the gravitational waves, all we need to do is to calculate the Riemann tensor and plug it into this equation. Now, we're going to calculate to leading order in h mu nu. So just linearized theory, assuming u nu equals 1, 0 to lowest order. That's to 0th order. Okay, so the idea is that this quantity is first order in h anyway. And so there's no need to consider anything else to first order in h. Everything else is going to be considered at 0th order, everything else on the right-hand side. Okay, so I'll just write that here. This is going to be first order in H. In H. And all of this will be 0th order in H. And on the left-hand side, I'm going to get the first order change in the separation vector due to that H. So we already worked out this mu nu rho sigma. It's equal to 1/2 H mu sigma nu rho minus H nu sigma mu rho minus H rho nu mu sigma plus H rho mu nu sigma. And in TT gauge, where H0 mu equals 0, there are no 0 components of H mu nu. You see, if U nu only has a 0 component, the spatial components are zeros, then all I'm going to need is R with 2 zeros down here. So the only thing I need is R mu 0, 0 sigma, because the only U0 is non-zero. And this is equal to 1/2. So I just need to look at these terms and see if they have any 0 indices on the H. And if they do, then they must be 0. So the only non-zero term is actually the first one, H mu sigma 0, 0. Okay, because nu is 0 and rho is 0, so this is 0, and this is 0. Okay, so what we get is that d2si dt squared is equal to 1/2 hij, comma 0, 0 times sj. The separation vector, the change in the separation vector, is given by the gravitational wave times the separation vector. So let's first do our gravitational waves, and then I'm going to point out something peculiar about this equation, which leads to a very interesting effect discovered by Christodoulou, who's a famous GR expert. You see, it's a little bit weird. The forcing term on the right-hand side involves a second time derivative of something. It's not a force, as we usually think about it, right? It's a second time derivative of something. And that leads to a consequence, which is called, I call it the Christodoulou effect, which is quite interesting. But before we do that, and for some reason the textbooks overlook this, don't know why, but it's actually a very interesting effect. Let's take our TT gauge gravitational waves, G waves, and we're going to take in the Z direction. Okay, so just as before, assuming the momentum is in the Z direction, then Hij is equal to just this 2x2 matrix, H plus minus H plus, Hx, Hx, times e to the I k dot x. Now let me just be careful. How did I define them as epsilon. Maybe I'll call them epsilons just to make clear they're constants. Okay, so the only quantity that depends on space-time is that quantity. And furthermore, in solving this equation, we can just take x equals 0. We can take the spatial coordinate x to be 0. In other words, I'll just pick coordinates so that the particle I'm calculating the deviation from is at the origin, right? So there's some other particle. There's a particle at the origin. It's another particle, and the location of the other particle is given by s, this vector s. And so I can actually set this argument, the spatial part of it, to 0 for the purposes of integrating that equation. There's nothing involving x in that equation. And so let's see what happens when I plug this into that equation. So first, assume only epsilon plus is non-zero. Okay, so that's one of the two linear polarizations of the gravitational wave. And then this equation, star, let's call that star. So star becomes S1 double dot equals minus k squared over 2, because I've got to differentiate my h twice with respect to time. And h goes like this, which is e to the I k naught t with a minus sign. Okay, so differentiate that twice with respect to t. I get a minus k squared. I get the half. I get epsilon plus. And then I get e to the minus I k t. And of course, what I should do is add the complex conjugate to h, because h is really a real thing. And so, for example, if epsilon, yeah, good enough. I mean, epsilon is a complex number, so that can contribute, of course, to the phase of the wave. But this is the right expression for S1. The solution, sorry, I left out the S1. Now, when you solve this equation, you see this is small. Epsilon plus is small. So what you want to do is take S1 to lowest order on the right-hand side, which is just some number, S1 of 0. So S1 of t is equal to the solution to this equation, where S1 of 0 is a constant. Sorry, let me write it down, and then I'll explain it. S1 is equal to S1 of 0. That's what it is to 0th order, times 1 plus epsilon plus over 2 e to the minus I k t plus complex conjugate. Okay, why is that true? Well, on the right-hand side, I just need to use the 0th order expression for S1. So on the right-hand side, I literally just have constant, because this is already, this stuff is first order. And then I integrate this up. So let's just check if it works. Put this into there. The double dot term, all I get is the double dot of this, which is minus I k squared over 2. And I get multiplied by S1, 0, which is the value of S1 at time 0. Actually, it's not the value of S1 at time 0. It's a constant. Okay. Constant. S1, 0. So let's say, take this to 0th order.
Is the value of
It's a constant. All right, it's just a constant. It's the zeroth order solution. So that's the solution for S1, and likewise, S2 obeys exactly the same equation. So S2 is S20 times 1. But the difference is that S2 is sourced by this guy, and I should have put a minus in here and not a minus there. You should have caught that. So this is 1 minus epsilon plus over 2 e to the minus I kt plus complex conjugate. So that's what the plus waves look like.
Neil,
Yeah.
if I differentiate S1
Yes.
or S2, let's put a minus IK out front of the
Yes. So for differentiate, I just ignore this term.
Pull a minus IK out of that term, I put a positive IK out of the next term.
No, I take it term by term. It's a linear sum.
Yeah. So I put a minus IK out of that term.
I get minus ik times minus ik gives me minus k squared.
No, but if I just differentiate it once,
Yes.
and then sub into equals 0, everything cancels.
This one and that one cancel.
Yeah.
Yeah, it's because they don't quite, actually. Okay, because this is complex conjugate, right? So this is epsilon plus star over 2 e to the I kt. Okay, so when you think of this as being real, then of course it's a cosine, and the dot vanishes at t equals 0. But if I make this not real, I can shift the phase of the cosine. So yeah, I haven't gone into that. And in fact, in Carroll's book, he's really pretty cavalier about all of this, and all of his equations are complex, and they don't really make any sense. But it's a very good book. I'm going to tell you something which isn't in his book in a moment. I do recommend, by the way, the section on gravitational waves in Carroll's book is pretty good. Seems to be better than other books. What's that?
He might be watching this.
I don't mind. He's a blogger, so he's used to free floating criticism. Okay, so that is that's epsilon plus is non-zero. So let's next assume epsilon cross is non-zero. Okay, and in this case, you find that the S1 double dot is now sourced by the S2, okay, because the metric is off-diagonal. So S1 is sourced by S2, and S2 is sourced by S1. And so what this leads to is that S1 of t is S2 of 0, S20, and again, a constant, times 1 plus epsilon cross over 2 e to the minus I kt plus complex conjugate, and S2 of t is equal to S1 0 times 1 plus epsilon x over 2 e to the minus I kt plus complex conjugate. So we can draw pictures of these two waves. As follows. So what you're supposed to imagine is a ring of test particles. And we'll choose this ring to lie in the xy plane. So ring of test particles. So let's choose them to lie along this ring. Like that. And then the gravitational wave is going to come along into, let's say, into the blackboard. And we want to know what's its effect on this ring. So the H plus causes the ring to do the following. It starts circular, but then it's stretched in one direction. Well, let me just draw it, the stretched version. Okay, so basically it's stretched up and down. It's compressed side to side. And then it oscillates back to a circle. And then it goes side to side. So when it comes back, it's going down, down, out, out. And so the H plus stretches space in one direction, squishes it in the other, and the stretching and compressing oscillates back and forth. Okay, the HX, so this is, I guess let me write it this way. The HX takes the circle and it does the same thing, but in the diagonal direction. So it will squish it this way, expand it that way, and then come back to circle, and now squish it in the diagonal and expand it that way. And so it goes like this. And it's also interesting to think about what circular polarization. And as you might imagine, the reason it's called circular polarization is that it stretches in one direction. So circularly polarized wave stretches the ring in one direction. It never takes the ring back to circular form. It stretches it in one direction, and this stretched direction rotates around. Okay, so it goes to this, it goes to this, just rotates like a solid body. No, I didn't draw that very well. Okay, so it just rotates the ellipse like a solid body. And that's what circularly polarized electromagnetic waves do as well. If you sit at one point in space, the electric field just rotates with the same strength at all times. And by the way, this is like string theory. In string theory, so actually, Carroll does mention this in his book, but I think he says it wrong. In string theory, a photon is represented, a mu is represented by a spinning piece of string with two ends. Okay, so this is open strings represent photons. And open strings, the ends of the string have to move with the speed of light. That's a boundary condition that follows from the variational principle for open strings. And so basically you have this rod which has to spin okay, one way or the other way. And in string theory, the motion of the string has to be perpendicular to its length, to the tangent vector along the string. So a photon is a spinning piece of string which moves at the speed of light, and it spins either clockwise or anticlockwise around its direction of propagation. And those are the two polarizations of a photon in string theory, going this way or that way. So that's a photon. The graviton, okay, tell me what a graviton is. The graviton is, in string theory, is an excitation of a closed string. It doesn't have any ends. So how can I make a closed string out of an open string? You should know this. Stick the ends together, right? So what I do is I take two photons and I just glue them at their ends. And that's a closed string. And what it does, it's got to move at the speed of light. So this is an open string. This is a closed string. And it's a graviton. And if this is spin 1, that's obviously spin 2. It's literally two photons, which are glued together end to end. Okay, that's what a graviton is in string theory. Okay, I said I would tell you about a nice effect of this equation up there. So this Christodoulou effect. Now, Christodoulou is a mathematician who writes tomes, okay? So he has managed to prove all kinds of theorems, existence theorems for solutions of the Einstein equations. But his work is very, very hard to read for a physicist, certainly, and I suspect also for mathematicians. It's to do with existence of solutions to PDEs, blah, blah, blah. He discovered an effect which, with hindsight, is completely obvious, and I don't know why it wasn't discussed earlier. It's just my own ignorance. But he was very excited about this effect, but it's completely obvious from that equation star. Christodoulou effect. If a pulse of gravitational radiation passes let's say impinges, I'm sorry to use an obscure word, impinges on a particle, okay? Then, so we're a particle sitting here, the gravitational wave comes past. The effect on the particle from there is that d2si dt squared, well, I can integrate that formula. So S, the change in the separation, will go like the double integral of this Si times H. Let me just see. Yeah, let me just say it can impart a net momentum to the particle leaving the displacement growing linearly in t. Okay, so when you look at that equation carefully and you work out the right-hand side, this particle is feeling a force, okay, and there's nothing in GR which forces the time integral of that force to be 0. And if the time integral is not 0, what happens is the particle, after the wave passes, has a net velocity. And so this is a non-vibrating term in the solution of the geodesic deviation equation, and that term can be created by gravitational waves. Yep.
The start equation, you've got a superscript I and a subscript I, so something's happened.
Say again?
In the start equation, you've got a superscript I and a subscript I, so something's happened.
Oh, yeah. I haven't been careful because that is to lowest order. Let's see, it was up there, it was up here. I mean, it doesn't really matter. The spatial indices up and down don't really matter because it's just delta. So if you want me to put it up, I can put it up. Doesn't make any difference. Okay. But for a pulse of gravitational waves, in general, the time integral of the pulse at a fixed location in space is not 0. And as this pulse passes, the particle ends up moving away. And so that's an interesting effect. And the net momentum acquired by the particle is a signature of the shape of the pulse. So there's a sort of extra effect in GR above what you get with electromagnetism. Are there any questions?
Wait, you can have a photon that hits a particle and... Oh, right, so you're saying the gravitational radiation doesn't change and it still imparts net momentum? How is this any different from like his photon?
No, it's true. A particle can also impart momentum. A photon can also impart momentum. It's true. Actually, I think that's not different. Yeah, it's a good question. There is some difference in the two cases. I don't remember precisely what it is. But in principle, there's no reason why a wave can't impart momentum.
Is the gravitational wave like, does it lose momentum as a result? I mean,
It must.
Yes.
yes. So
It has to.
you can think about it as like it's the normal like
Yes.
diagram of being
A Feynman diagram. Yes, you can.
Is the momentum in the direction of the propagation of the wave?
Yes, it would be. I mean, the change in the particle's momentum would be, yeah.
So why is it so hard to gravitational waves? This effect.
Because the H is so tiny. Okay, so the kind of H which LIGO is trying to detect, is designed to detect H's down to 10 to the minus 20. Okay, so it really is a tiny effect. And even if you give the particle a kick, it's a kick of that order. So it's really very, very hard to detect. Even though LIGO is 1 kilometer long, it's trying to detect displacements which are, 10 to the minus 17 of a meter. It's much, much smaller than an atomic nucleus. I mean, that's 1/100th the size of a nucleus. You could say, how on earth do they detect lengths so small? And they do it by averaging, because it's a big object. And so even though the position of any nucleus could never be measured to that accuracy, when you average over billions of nuclei, the average position can be measured to that accuracy. And they're all moving the same way.
Can you make such a setting that you can be sure that whenever we detect that displacement, then it's due to gravitational waves? Because, like, you know.
No, you can't. I mean, there are vibrations, there are all kinds of other things. Yeah, they have. They've been working on this for 20 years, or longer, actually, since the 1960s. The first claim of detection of gravitational waves was in the mid-60s by Joe Weber, and he made a big metal bar, and he claimed the length of the bar was vibrating due to gravitational waves. It's a bit like BICEP. You know, but it was the beginning. I mean, there's a plus and a minus. He started the field, right? He got everyone excited. So everyone else started chasing for the same signal. And they used better experiments, and they found it wasn't there. But the experiments got better and better and better. And we hope that in 5 years' time, they will find gravitational waves. Okay, but it takes a long time. I mean, this is, you know, almost, we will see gravitational waves sort of almost 50 years after that first claim. So it's good to get everyone excited, but one should bear in mind that the first claim detection is not always right. And, you know, in the case of BICEP, it's a considerably bigger claim. Because Joe Weber knew that there are black holes and neutron stars, and, well, he actually didn't know about black holes, but he knew that there were neutron stars and objects running around the universe. They almost certainly give gravitational waves, so his claim was pretty modest. To claim to see the Big Bang at, you know, 10 to the minus 30 seconds is a very big claim. The amazing thing is that by and large, the physics community bought it. People were amazingly accepting and uncritical. It's a problem. People seem to have lost their ability to question. So anyway, science is self-correcting, luckily. That's what I was sending my email. I was sending my email to The Economist magazine, who's interested in the BICEP. What does it mean? Has it all gone? And all that stuff. So yes, it's all gone. Any other questions? Okay, so next lecture we will fall into a black hole.